All right. We have just checked our homework. We're getting ready to do, starting on page 126 in our science book, Characteristic of Stars. We're going to do just about half of the chapter. Watch a couple of videos that I will give you the links to, and you'll be good to go.
Isn't this what we're reading tonight?
Yes. Just set it up there. He'll be back in here in a minute. All right. All right, first thing we're going to do, okay? Take your thumb, this session, you've probably done this before. Pick out something somewhere in the room and put, and shut one eye and put your thumb over it, okay? It could be one of the plugs on the wall, and stretch your arm all the way out, and then open the other eye, shut the other eye and open this one, okay?
Oh yeah, I do this all the time.
You notice it's off a little bit. Now, do the same thing, but bring it in a little bit. And it's off even more. Okay? And if you do the other eye, it goes the other way.
It's a little bit off. I'm doing it on your face, by the way.
Well, it's off anyhow, so that's right.
See, one day I was like,
Okay?
because like one time like I was just playing around and I was just like this, and then okay, so I was like pretending I don't even know what I was doing, and then I switched my other eye and I'm like, wow, I was off by a lot.
It's weird, yeah. It's weird. It's
That's
off.
why when you shoot something,
All right.
it moves.
All right. Calm down. All right. Now, while ancient observers around the world looked up at the night sky, they imagined a group of stars that formed pictures of people or animals. And of course, today we refer to those as constellations. Or sometimes we refer to it as spheres. Put up the book that you're reading and pay attention. Hey, he likes to read. Okay?
The only thing I
Now,
have to say to that is stop drawing during class.
I know, he's sitting there drawing pictures. You're reading books. So it's really not any difference. All right.
Pulling that card. It
All right.
helps you focus.
Stop. Different cultures give different names to the constellations. For example, large constellations in the winter sky is named Orion. Okay, most of you have probably looked up at some point in time, and someone pointed that out to you. You might now be able to identify. Okay, but it was Orion the Hunter. He was named after a Greek myth. Okay, in this constellation, Orion is seen with a sword in his belt, an upraised arm, supposedly holding a club. You can usually tell him by his belt, though. Okay, he's got the 3 stars that makes up his belt, and then the sword that hangs down, and it's easier to see that way.
It's like some of the constellations, like that the Greek or Romans named, like I can see it, but like Orion, I would not look up at the sky and see this whatsoever.
No, it's like I say, I can identify the belt, and I know that's Orion, but I do not see, I can't make out the guy standing there holding a club with a sword and holding a shield and all that.
Yeah,
that's a little tougher to see. So good imagination, grape juice, I don't know, something was involved here that helped with these visions. Okay? Now, they do use the patterns of the constellations to locate objects in the night sky. Okay? Although the stars in the constellations look as if they are close to one another, they usually are not. Okay? Just because the stars are in the same area of the sky doesn't mean that they're side by side. They might be light years away, but they just happen to line up that way. Okay? So keep that in mind. Okay? The way they classify stars, like the sun, all the stars are huge spheres of glowing gas. They were made up mostly of hydrogen, and they produce energy through the process of nuclear fusion. If you remember when we talked about the sun, okay, that's what stars do. Yes?
If we could harness the energy of like the sun or a whiteboard, then we would have enough energy to power the entire world.
Yeah, what was it they said? If you could harness the energy of the sun for just a few seconds, you could power the Earth for, I forget how many years it was that you could actually power the Earth.
That's insane.
So, yeah, it is insane.
You
And we're
would
not
have to
talking
pay
solar
electrical
energy
bills.
here, we're talking if you could actually get that power that it is producing.
Like electrical bills would
Yeah.
have to go down because it's so easy to get the power now.
Yep. Okay, so the energy makes stars shine brightly. They classify the stars according to their physical characteristics. And here's the characteristics, okay? Color, temperature, size, composition, that means what they're made out of, and brightness. So there's 5 things there. That's how they can the characteristics of a star. Okay? The color and the temperature. If you look up at the night sky, you can see the difference in the colors of the stars. For example, Betelgeuse is the bright star in Orion's shoulder. Okay, you see the belt. You'll see the belt here, and we're going to point this out in one of our little clips. You see the star, but if you go straight up, and Betelgeuse actually is that bright star that makes up his shoulder. Okay, and it looks kind of reddish. Okay. Regal, the star, or Regal, I think they refer to it, is the star in Orion's hill. It is kind of a blue-white. Okay? Now, like hot objects on Earth, a star's color actually reveals the surface temperature. Okay? If you watch a toaster at your house, if you're toasting bread and you turn that on, it glows red, right? Yeah. You look at a light bulb, and inside of it, it's actually white. It's burning more white, okay? That light bulb is actually hotter than the toaster, okay? It's actually burning hotter. Really? Okay?
Have you ever touched the Lego?
Now, similarly, the coolest stars with a surface temperature of about 3,200 degrees Celsius appears reddish in the sky, okay? When the surface temperature reaches about 5,500 degrees Celsius, it turns yellow, like our sun, okay? The hottest stars in the sky, with a surface temperature of over 20,000 degrees Celsius, actually appears to be blue. They are burning super, super hot at this point in time, okay? So that's the different colors that you're going to see. So kind of keep that in mind, okay? It's going to come in handy. When you look at stars in the sky that appears to be points of light of the same size, many stars are actually about the size of our sun, which is actually just a medium-sized star, which we've talked about. However, some stars are much larger than our sun, which we have seen that also in some of our videos. Our sun would just pale in comparison. It'd just be a dot on some of these massive stars out there. If the supergiant star Betelgeuse were located where our sun is, it would be large enough to fill the solar system all the way out to Jupiter. Okay? That's a long ways out. Okay?
Would that be a giant
And
star?
that's if that's a giant, yep. And they do classify them as giant stars and supergiant stars. I love how they get scientific on some of the names. You know, the core, the inner core, the inner core. Then we got giant and supergiants. Okay, so.
Yeah, like some of the things that
And then they'll name something else very simple, some Latin name that I have no. I'm sitting here struggling trying to.
I know, but we can go like we have such hard names, like you don't even know what I mean. And then you have giant.
Yep. Yep.
And then this one's super giant.
Okay. So most of the stars are much smaller than the sun. White dwarf stars are about the size of Earth. Neutron stars are even smaller. They can be about 20 kilometers across or in diameter. Okay? Yes, Braxton?
That star Betelgeuse. So that'd be a giant star.
Uh-huh.
And then,
What would be a supergiant star then?
yeah.
What's the biggest one out there? Remember it?
It was like the one that you couldn't even mark the sun on
Yeah,
because of.
that's a supergiant.
Wait, what was his name? No, you could put a Sharpie dot on it and have it.
And it wouldn't represent that.
You could
Wait, what
put
was his name? I can't remember his name. Super giant.
No, the name of the star, like the big star we found.
What is it? Canis Majora? Is that it?
It's something like that.
Okay.
The
So, the chemical composition. Stars vary in their chemical composition. Now, this starts to get a little bit more complicated. Okay, so pay attention. The chemical composition of most stars is about 73% hydrogen, 25% helium, and 2% other elements by mass. Now, this is very similar to the makeup of our sun, okay? They use this thing called a spectrograph to determine the elements found in stars. Now, this thing, a spectrograph, is a device that breaks light into color and produces an image of the resulting spectrum, okay? And most of the large telescopes in these observatories has a spectrograph built into it, so when they're looking at it, they actually can pick up and break down the composition of these planets or these stars. The gases in a star's atmosphere absorb some wavelength of light, produced within the star. When the star's light is seen through the spectrograph, each absorbed wavelength is shown as a dark line on the spectrum. Okay? Each chemical element absorbs light at a particular wavelength. Just as each person has a unique set of fingerprints, and you guys do realize your fingerprints are different than everyone else's. Okay? They are uniquely yours. Okay? And even yours are different from finger to finger. Okay? They might be very similar, but they are different. Okay? That's why they can use fingerprints to identify you. That's why, like, the police officers will take fingerprints at a crime scene and run it through, and if you know you have been fingerprinted before, it will come up.
When do you
And they can do that.
Do you get fingerprinted when you're born? Or?
No.
Because that would be an easy way.
I got fingerprinted at safety town.
Yeah,
I must have.
stop. They fingerprint you if you're arrested for something. They obviously fingerprint you. If you go in the military, they will fingerprint you as a way to identify you. All right. So now,
That's basically
the lines of the four elements. It's got the pictures here that kind of shows you how it breaks it down. You need to stop talking and listen to what I'm saying. Okay. By comparing a star's spectrum with the spectrums of known elements, then they can infer how much of each element is found in a star. Okay? So they can actually break it down just by looking at different wavelengths and picking up colors. And they have compared that to that element, and they can now break it down and tell you how much each element is in a star. That's pretty cool. Okay? All right. The brightness of stars. This is pretty good too. Stars also differ in brightness and the amount of light they give off. Okay? The brightness of a star depends on both its size and its temperature. Okay? Size and temperature. Remember that the photosphere is the layer of a star that gives off light. Okay, so Betelgeuse is fairly cool, so a square meter of its photosphere doesn't give off much light, but because it is so big, it shines very, very brightly, okay? So if you took off just a very small portion of it, if you took off a square meter of Betelgeuse, it's not that bright. But you put them all together, and it is one of the brightest stars out there because of its size. It's so massive. Okay? Rigel, on the other hand, is very hot. So each square meter photosphere that it gives off gives off a lot of light, even though it is smaller. Okay? It actually shines more brightly. Yes?
Nice question.
Sure. So, how bright a star looks from Earth depends on both its distance from Earth and how bright the star truly is. Because of these two factors, the brightness of a star can be described in two ways: apparent brightness and absolute brightness. Okay? These are things you're going to want to remember. Okay? You want to see these again. Okay? Apparent brightness is the brightness as seen from Earth. Okay? It appears to be bright, or it appears not to be as bright as that one over there. Okay? So they can measure apparent brightness easily using electronic devices. However, they can't tell how much light a star gives off just from the star's apparent brightness.
Isn't it because they probably are a million miles apart and maybe
Exactly.
farther away?
Just as a flashlight looks brighter the closer it is to you, okay? I got a little flashlight up here. If I stood up here, we turned off the light and I stood up here with my little flashlight and shined it, and you're standing in the back of the room, it's going to look bright, but it's not going to look as bright. But if I walked up to you and got, within 3 inches of your face, all of a sudden this is a very bright little flashlight, okay? So the closer it is, the brighter it's going to appear, okay? So, and that's why that's the way apparent brightness works, okay? The sun, for example, our sun looks very bright. This doesn't mean that our sun gives off more light than all the other stars. It just means that it's closer to Earth than any of the other stars. Okay? Now, absolute brightness is where it kicks in. A star's absolute brightness is the brightness the star would have if it were at a standard distance from Earth. Okay? Finding a star's absolute brightness is more complex than finding its apparent brightness. As an astronomer must first find out both the star's apparent brightness and the distance from Earth. Okay? So they got to take both of these things in. Now, how do you think they could calculate this out? What science would they have to use? What do you think? Math. Yeah. Math is a science. Okay? It is an absolute science. One of the few absolute sciences there is. Okay? It's either right or it's wrong. Everything else can be theories. Math, same. It's either right. It is, yep. Okay? So, they have found that absolute brightness of stars can be vary tremendously. The brightest stars are more than 1 billion times brighter than the dimmest stars. 1 billion times. That's a bunch. All right. We're going to watch the videos now.